Assalamualaikum and hi everyone. Let us learn chapter 11, Nuclear and Particle Physics. This is last chapter for SP025 and for paper 2, 7 marks will be allocated. Let us look nuclear structure, combination of proton and neutron, we call it nucleon. Whereas here is electron, which is always orbiting along this nucleon. However, the chemical symbol for nuclide, we use X, okay, and A is represents for mass number, or we can also use as nucleon number, whereas Z is atomic number and known also as proton number. Proton and neutron actually characterized by following properties. You can see here proton charge, and for proton charge we have 1.6 times 10 to the power of negative 19, and for neutron it not have charge and we call it uncharged, while for a mass for proton is 1.672 times 10 to the power of negative 27 kg, and for neutron is 1.675 times 10 to the power of negative 27 kg. Actually, all the nuclei in periodic table have its own symbol based on atomic number, a neutron number, and a mass or nuclear number. So if we look at this symbol for atomic number, we use Z, okay, which is referred to atomic number or known as proton number, and we have N, neutron number, and we have a mass or nuclear number which represents A. So you have to remember also relationship between A, which or mass number, which is equal to combination of atomic number plus neutron number. Any nucleus elements in periodic table, also called nuclei, which is characterized by Z and its mass number as A, and the nuclide of element can represents as X, okay, and A is referred to the mass number and Z is atomic number or known as proton number. And this element is very important to remember. Okay, if you look at for carbon, we have carbon 12-6 and rubidium, which is 3785, and you can see its chemical symbol of this radionuclide. Okay. (11.1) Binding energy and mass defect. We have four learning outcomes. First is you need to define and use mass defect. The equation is delta M equal to ZMP plus NMM minus M nucleus. Okay, so this is very important equation for you to know. And you need to define and use binding energy. We have binding energy E equal to delta MC square, and you need to determine binding energy per nucleon, or we use EB over A. Okay, sometimes we use EB over A, and then you need to sketch and describe graph of binding energy per nucleon against nuclear number. Mass defect of the nucleus, it is defined as mass difference between total mass of constituent nucleons and the mass of nucleus. So the equation that we use is delta M equal to ZMP plus NMN minus mass of nucleus. Dear student, you have to concern with the equation of mass defect. Okay, like as delta M is referred to mass defect, ZMP, Z the number of protons in nucleus times mass of proton, right? Plus N is represents for number of neutrons in a nucleus times mass of neutron minus mass of nucleus, or we use capital M nucleus. Actually, the MS nucleus is always less than the total mass of its constituent nucleons, right? So reduction of mass arises because of the act of combining the nucleons to form the nucleus. So any attempt to separate the nucleons would involve them this same amount of energy, and this energy is called binding energy. Nuclear binding energy. Nucleons is a stable nucleus and held tightly because of it has strong nuclear force. So we need energy which required to separate a stable nucleus into its constituents, protons and neutrons. So this is the figure that's showing you nucleus plus binding energy, which you use delta mc squared, and this is the figure showing you separated nucleons after we combine the nucleus with this binding energy. In other words, the binding energy of nucleus is defined as the energy required to separate completely all the nucleons in the nucleus. And binding energy of nucleons is equal to the energy equivalent to the mass defect. Regarding to the formula of EB equal to delta mc squared, EB is binding energy in unit joule, delta M is mass defect in unit kg, and C is speed of light in vacuum. Here are unit conversion of mass and energy. 1 electrovolt actually is equal to 1.6 times 10 to the power of negative 19 joule. And 1, if you want to change it to mega electrovolt, 1 mega electrovolt is equal to 10 to the power of 6 electrovolt, which is also equal to 1.6 times 10 to the power of negative 13 joule. And if you have atomic mass unit, means you are not using for mass unit, you are not using kg, you use U, and U is also known as unit of mass. It is defined exactly 1 over 12 the mass of neutral carbon 12 atom. Okay, so this is the equation that's showing 1U, which is equal to mass of carbon 6 over 12. U, or atomic mass unit, can be converted into unit of energy by using the mass energy relation. Since we know the energy is equal to mc squared, you know the M is mass, which is 1.66 times 10 to the power of negative 27 kg times c squared, 3 times 10 to the power of 8 squared. You'll get the energy which is equal to 1.49 times 10 to the power of negative 10 joule. And if you want to convert from U to joule, you can times 1.49 times 10 to the power of negative 10 joule. If you want to convert from joule to U, you need to divide by 1.49 times 10 to the power of negative 10 joule. Besides that, you can also get the energy in unit electrovolt by using 1.49 times 10 to the power of negative 10 joule divided by 1.6 times 10 to the power of negative 19. And you will get 931.5 times 10 to the power of 6 electrovolt. So you have lots of choices to choose to convert the unit of energy based on mass energy relation. Besides, you can use from U, if you change it to electrovolt per C square, you can directly times 931.5 times 10 to the power of 6. So you can get from U directly to EV per C square. Or if you want to change from 1U to mega electrovolt per C square, you can directly times 931.5. So you will get 931.5 MeV per C square. Binding energy per nucleon, actually the binding energy per nucleon of nucleus is equal to EB over A. A is stand for nucleon number. So you can also use regarding to the binding energy, which is delta N C square divided by A. So binding energy per nucleon actually that determines the stability of the nucleus. This is graph of binding energy per nucleon against nucleon number, or binding energy per nucleon known as EB over A, but we are using unit MeV per nucleon. And if you look at the binding energy per nucleon is increasing, starting from hydrogen, lithium, carbon, nitrogen, gallium, until it reaches ferrum. Ferrum is the stable condition for binding energy per nucleon. It's very stable, and followed to arsenic, and until it reaches uranium, the proton decrease smoothly. This graph shows binding energy per nucleon as a function of mass nucleon number, or A. Okay, that I said just now, the ferrum is very stable, followed to here nickel. The mass number is around ferrum 56 and nickel is 62. Okay, this is very stable, and the explanation you can read here. Let us learn radioactivity, learning outcome 11.2. You need to explain alpha, beta plus, beta minus, gamma decays. The second one, you need to state and use decay law, dn over dt, which is equal to negative lambda n. C, you need to define and determine activity and decay constant, lambda. D is you need to use n equal to n naught epsilon negative lambda t, or A equal to A naught epsilon E minus lambda t, and to define and use the T half, or known as half-life, which is ln 2 over lambda. Radioactive decay, it is defined as a spontaneous disintegration of unstable atomic number accompanied by radioactive radiation such as alpha particles, beta particles, and gamma particles. And it is spontaneous reaction, means it's unplanned, cannot be predicted and independent of physical conditions such as pressure, temperature, and chemical changes. Radioactive decay is a random reaction because it is impossible to predict the decay of individual atoms. Popcorn is analogy for radioactive decay. We know that the popcorn will go pop, but we don't know exactly which kernel will pop at any given time. Radioactive decays, we have alpha particles, we have beta particles, but beta we have two types, beta minus and beta plus, and the third one is gamma rays. This is a radioactive decay. The unstable nucleus disintegrates spontaneously and randomly. Certain kinds of particles or high energy photons are released, such as alpha decay. We have two types of alpha decay. New nucleus that produced from the uranium decay is strontium, and helium is from reduction. And gamma decay will produce relaxed nucleus. And beta minus decay, we have carbon 14, which produce nitrogen 14 plus antineutrino and electron, while for beta plus decay, it produces boron 10 plus neutrino and positron. Alpha particles. Alpha particles consist of two protons and two neutrons. Example, helium for 2, or you can use alpha for 2. And it is positively charged, and its value is positive 2A with a mass 4.002603 U. And this is the equation for alpha decay. So we have radionuclide X, okay, known as parent, will produce Y, known as daughter, plus helium or alpha particles and heat. Same also to radium, which is produce radon plus helium and heat. This is the figure how the radium produce radon and helium. Besides, you can see few equations related to the alpha decay, such as polonium, thorium, and uranium. Polonium will produce plumbum and alpha decay, thorium, radon, and helium, while uranium is thorium and alpha or helium plus heat. As we all know, for beta particles, it's divided by 2. First is beta minus, and the second is beta plus. The beta minus known as electron, while beta plus is known as positron. Beta minus you can use electron 0, negative 1, or you can use also B minus. While for beta plus, you can use electron 0, 1, and you can put beta plus. And this is the production from decay process from parent X, nuclide X will produce Y, which is Z plus 1 plus electron, which is beta minus, plus anti-neutrino, or you can see V bar. And this one is parent nuclide will produce for beta plus A minus 1 Y plus electron, or you can use beta plus 0, 1 plus neutrino. So these are different of beta decay. This is example of beta minus and beta plus. So you can see the carbon plus will produce nitrogen plus electron and antineutrino. Means that for electron, all the uh, all the beta minus will produce uh, antineutrino, and for beta plus it will produce neutrino, and the parent nucleus has more protons than neutrons compared to the beta minus. Parent nucleus has more neutrons than protons. Neutrino and antineutrino, it is introduced to account for missing energy in beta decay. Properties of neutrino and antineutrino: it has zero electrical charge, mass much smaller than the electron, probably not zero, and its spin of half, and very weak interaction with matter. Actually, the electron emitted in beta decay is not an orbital electron. The electron is created in nucleus itself, and these particles are referred to the beta particles so as not to confuse them with the orbital electrons. Gamma ray. Gamma rays are high energy photons, or known as electromagnetic radiation, and it does not change the parent nucleus into a different nuclide. Its nucleus is an excited state, makes a transition to a ground state. Examples of gamma is polonium, which produces plumbum and helium plus gamma, and protactinium, which will produce uranium plus beta minus or electron and gamma. And we have tritium, which produce tritium and gamma. So these are gamma ray, and it is uncharged neutral ray, and it has zero mass. Radioactive decay. Regarding to the law of radioactive decay, decay rate is directly proportional to the number of atoms and which present at instant. So you can use negative dn over dt is proportional to n, and besides that you can use dn is equal to negative lambda n dt. So the constant of proportionality is called decay constant. Decay constant, or lambda, is equal to negative dn over dt, or radioactive decay rate, divided by number of remaining nuclei, or n. And definition for the decay constant, it is a ratio for the number of atoms of radionuclide that decay in a given period of time compared with the total number of atoms of the same kind present at the beginning of the period. And it is also called disintegration constant or radioactive constant. Just now, I show you dn is equal to negative lambda n dt, and negative dn over dt is equal to lambda n. If you look at here, negative dn over dt, it is referred to the activity, which is also equal to lambda n. And we can define the activity as disintegrations per second by the radioactive nucleus, and the standard of unit for activity, you have to use becquerel. And Curie, if you have a question, give activity in unit Curie, you have to convert it to becquerel. Guys, 1 Curie is equal to 3.7 times 10 to the power of 10 becquerel. From law of radioactive decay, Tn over dt equal to negative lambda n. So, by rearrange this formula, Tn over n is equal to negative lambda dt. So, let us integrate this equation from t equal to 0 when n equal to n naught to t equal to t and when n equal to n. So we can say ln n minus ln n naught is equal to negative lambda t. Ln n over n naught is equal to negative lambda t, and n over n naught, if you want to use n over n naught, you can put the epsilon here to your right side, which is epsilon negative lambda t. By rearrange this formula, makes n as a subject, n equal to n naught epsilon negative lambda t. Same also if you have case activity. Activity is known as lambda n. So A is equal to A naught epsilon negative lambda t. Decreasing of the radioactive nucleus number is exponent to this time. Half-life is time taken for half of the initial number of radioactive elements to undergo decay. T half is equal to ln 2 over lambda. Introduction to particle physics. In this learning outcome, you need to state the thermionic emission. You need to explain the acceleration of particle by electric and magnetic field. You need to state the role of electric and magnetic field in particle accelerators, such as LINAC and cyclotron, and detectors with general principles of ionization and deflection only. You need to state the need of high energies required to investigate the structure of nucleon. You need to indicate a standard quantum lepton model particles such as baryons, mesons, leptons, and photons. And you need to explain the corresponding antiparticle for every particle. Let me introduce you with particle physics. Physicists use particle accelerators to explore matter on the smallest scale, and the charged particles such as electrons or protons are accelerated by an electric field to speeds almost equal to the speed of light. They are made to collide with one another, and in such collision, some of the kinetic energy is turned into matter, which new particles are created. Thermionic emission. It is simplest particle accelerator is electric gun, and electrons are produced by heating a cathode. Okay, this is cathode. Electrons boil off from the cathode and accelerated towards an anode with a small hole in it. And many of the electrons pass through the hole, forming an electron ray, which is cathode ray. Let us look particle accelerators. Basic types of particle accelerators such as linear accelerator or known as LINAC, and the second one is circular accelerator. For linear accelerator, it is propel particles along a linear or straight beamline and are used for fixed target experiment. Whereas for circular accelerator, it is propel particles around a circular track and used for colliding beam and fixed target experiment. Linear accelerator, or known as LINAC, is from high frequency supply to target. It is an alternating potential difference which is connected across adjacent cylindrical electrode tubes, and charged particles accelerated across the gaps between the electrodes. By the time the particle reaches the next gap, and the polarity of electric field has reversed, and so the particle is accelerated. However, the length of LINAC limits the energy achieved, and one of the most powerful LINAC is located at California, US. LINAC SLAC, known as SLAC, stands for Linear Accelerator Center, and the SLAC is actually 3 kilometers and accelerates electrons up to an energy of 50 giga-electrovolt. Okay, besides LINAC, we have circular accelerator, or known as cyclotron. And for this cyclotron, it has length, which is limitation, length limitation, which can be overcome by making the charged particles follow a circular path. And charged particles are accelerated across the gap between two D-shaped electrodes, and its perpendicular magnetic field move the particles in a circle. This is magnetic field, and this is the beam of positive charge, which is moving to the T from D2 to T1, and this is the ion source. Regarding to the D shape just now, the radius of a circular increases each successive acceleration, so the spirals out from the source of the center to the target on the outside, and the small size of cyclotrons makes them useful for producing energetic particles for medical treatments and testing advanced industrial materials. Let us investigate the structure of nucleon. It is come from the scattering of high-energy electrons by nucleons. As we all know, the nucleon is the combination of protons and neutrons, which can reveal the internal structure of these particles. And besides, diffraction of particles depends on their wavelength, where it's more energetic the particles, the shorter the wavelength, finer the detail that can be observed, and it has very high energies which are needed to probe the very internal structure of proton and neutron. Quark. Quark is an elementary particle and a fundamental constituent of matter. And if you look at this figure, we have atom. Inside the atom, we have neutron and proton. We have neutron and protons. Inside the proton, I take out this proton out. Okay, you can see inside this proton, we have up quark, 2 up quark, and 1 down quark. Okay, so all this combination is known as quarks. If you want to know about neutron have 2 down quark and 1 up quark, while for antiproton it have 2 u bar and 1 d bar quark. However, for antineutron it have 2 down quark plus 1 up quark. This is the standard model of particle physics. Okay, the standard model categorizes fundamental particles into related groups, as seen in this table. We have elementary particles such as fermions, bosons. Okay, we have two types. And fermions, we have up, U stands for up, C, we have charm, T, we have it's referred to top, D is bottom, S is strength, S strange, and D is down. So these are quarks. Quarks have UCTDSB, while leptons is under fermions also. But lepton have electron neutrino. It have the symbol is Ve. It also have muon neutrino or V mu. It also have tau neutrino, okay, V tau. It also have electron E, muon mu, and tau. The symbol is tau. That is under leptons. However, the second type of elementary particle is bosons. In bosons, it have force carriers such as gamma, gluon, weak force or Z0, and weak force W plus minus. And under boson also we have Higgs. This is the simple particle classification. For particle, we have two types, leptons and hadrons. Leptons have three types, electron, muon, and neutrino, while hadrons has two types, mesons and baryons. For meson, it have two types, which is pion and kaon, whereas baryons, we have proton and neutrons. These are examples of hadrons. Particles of matter and antimatter, we have divide by opposite and identical, opposite based on charge and identical based on mass. For matter particles, we have such as electron, protons, and neutron. Antimatter particles such as positron, antiproton, and antineutron. Okay, these are particles of matter and antimatter. That's all. Finish for this chapter. All the best. Bye.